Okay, thanks very much for having me and giving me the opportunity to speak here. And so I will be talking about, as Björn said, relative TR and the Rham Witt complex. And most of this talk will be something a lot of you have me already seen speak about, like or announced these results a couple of years ago. But in the meantime, there has been a bunch of developments, and I sort of want to explain this ground off. Also because I feel there's a lot of, maybe I want to emphasize a little bit the equivariant aspects of the story, which are subtle, and usually I usually sort of keep that under the rug, but I feel like it would be nice if we sort of could connect that to some of the developments in equivariant TR that we've seen in the last years. Okay, so the first theorem that will occupy most of that talk is the following result. And this is in some version due to Hasselholt-Madsen, then Johan Mao has a version who's in the audience, and Konrad Bahls and myself have a version. And the goal is I will write down the result now here, and then I explain it, and then I will sort of explain what it has to do with crystalline comparisons of prismatic cohomology. So R is an ordinary smooth K algebra. So these are all like ordinary rings. Then there exists a p-cyclotomic spectrum that I denote THH R relative cyclotomic K with an isomorphism TR star of that cyclotomic spectrum. And so I'm going to explain what p-cyclotomic spectra are and TR are to make it possible to understand what I'm saying here. Just wanted to get the result one result out of the way first. That this is isomorphic to omega star W omega star R relative K. So I'm going to say this is the Rham Witt complex, P-typical the Rham Witt complex. I will also explain that. Rham Witt complex. And this is P-typical TR. And so P is going to be one prime that are fixed throughout. But I'm not assuming that any R or K is like P local or P complete or anything. And then, I mean, in stages, I will explain how the result was historically came about. And so this is like, in my opinion, the most general version where no assumptions on R and K. Okay, good. Let's get into what these words here mean. So first definition. Let's recall what a p-cyclotomic spectrum is, and I'm going to drop the p, so I'm going to say it this one time, and from then on everything is going to be p-cyclotomic. Is a spectrum X with S1 action, and that means in the naivest possible sense for L, S1 action together with an S1 equivariant map phi from X to X Tate CP. That's the Tate construction with respect to CP. And I want to make this convention that I put square brackets somewhere. And this will mean, so this is kind of a naive-ish definition. It doesn't really use equivariant homotopy theory. Of most of the things I'm going to say, there's going to be an equivariant version. So let me put the equivariant versions of that in the square brackets. So if I wanted to say this equivariantly, then I would say a S1 spectrum with respect, I guess X, with respect, or genuine, with respect to the family of P subgroups of S1. So I guess all CPn in S1 together with an equivalence of the geometric CP fixed points of X with X. And the square notation means these two categories are essentially equivalent. And I mean, I guess most of you know the fine print bounded below, then the two categories are equivalent. Okay, and here, I mean, it's important that this is like, again, an S1 spectrum. And the same is true here. So you have to use the residual actions. Okay, and so that's the first layer here, a p-cyclotomic spectrum. What's the second layer, TR? What is TR? TR is something associated with any cyclotomic spectrum. So what is the definition? It's another spectrum, TRX. And you can build it from this datum here. So what you do is you take a huge iterated pullback. So you take X, and you take the pullback over X Tate CP, where this map here is the phi map. And then you take X homotopy CP. And this map here is the canonical map. And then you can iterate this. You can again take X Tate CP upper H CP. So again, in this direction, take the phi map. And by virtue of the fact that this is equivariant, you get something on the homotopy fixed points. And then here you have homotopy CP squared fixed points, where this is the canonical map again. And you keep going. So in the somehow right down, it's always the phi map, and left down, it's always like the canonical reduction map. Okay, so that's the definition of TR, and I mean, really, you define this for finite things, and then it's an inverse limit, of course. That is the definition of TR. And this one actually looks a little bit more nice in the bracketed perspective, where it is just given by the inverse limit over the fixed points. So if you have a spectrum like this, X, then you can just take the fixed points. You take X, I guess, CP, and then X CP squared. And what is this map? I mean, if you have this map phi, there's always a canonical map from the fixed points to the geometric fixed points, and then you can compose with this map. That gives me this map, I guess, X upper E, I can put if I want. And then this gives me this map, and then you just do the same thing on the fixed points again. So you get this inverse limit, and that is TR. Okay, cool. So that's what TR is. And the classical examples that many of you know, and I guess we have Mona heard talk about it. I mean, the example of a cyclotomic spectrum, the prototypical example, of course, is if R is, say, a commutative ring. I mean, that can be associative. Then THR is an example of a p-cyclotomic spectrum. And I want to say this in a specific way. THR is R to the tensor S1. So it's a colimit in the category of E-infinity rings over S1. And why am I saying this way? Because this makes it clear it's the initial ring spectrum, say commutative ring spectrum under R with a map with an S1 action. Right, so this initial thing will be important in a second. That's why I wanted to recall that. And I mean, using this universal property of this being initial, it's not so hard to define like the cyclotomic structure. I don't want to go into this now, unless there's a question. Okay, what is not an example? A non-example of a cyclotomic spectrum is if you do Hochschild homology. So R is now commutative K algebra. Then you can do THH R relative K, which I guess you can also write Hochschild homology R relative K, which would be defined, if I now think of it over spectra, I would just define it to be R, and then I tensor over K with S1. Right, you can do this in every symmetric monoidal infinity category. Here I do it in the derived category of K. Here I do it in spectra. And so what is this? What is the universal property of this guy? It's the initial commutative ring spectrum under K with a K-linear S1 action. Right, so the only difference is that here I'm forcing my S1 action to be K-linear, where here I don't. And
should be under R.
Under R, thank you. Yeah, I never know whether to say under or over. It's a confusing thing in algebra. With a map from R. Let me say it like that. Okay, and the problem, I mean, why is this a non-example? The point is that you cannot define a cyclotomic Frobenius, the map phi, in a coherent way on this. Like, one can try, but it will not work out. It probably cannot be done. Unless, I guess, in special cases where, say, P is invertible in R, or so, in which case the Tate is 0. Like, if not for Tate being 0, you cannot define the cyclotomic structure. Okay, and that's a problem because somehow, I mean, I don't know whether that's a problem or not, but somehow the cyclotomic structure is, for example, obviously used to define TR and also invariants like TC. And so these are the invariants we want to consider with cyclotomic spectra, so we can't do it in such a relative setting. And in some sense, if we stare at the theorem up there, this is why I put this little cyclotomic over the slash. It's kind of getting rid of that problem and defining a cyclotomic variant of the spectrum. This is maybe in some sense what this talk is trying to achieve, or what this whole construction is trying to achieve. But let's review some calculations of topological Hochschild homology, Bergstedt and Hesselholt, and I guess I'm sticking to ordinary rings for this talk, so let me maybe stick with the classical calculations, and I guess I should mention BMS. So classical case is FP. So if I write THH star, I just mean the homotopy groups of THH. And in this case, I mean, THH, of course, is a commutative ring, and the graded homotopy ring is just FP adjoint X, where X is an element in degree 2. Sometimes called the Bergstedt element. And then the cool thing is that happens is if you then compute TR, then actually you get that this ends up being discrete. So it's a ZP in degree 0. So as a spectrum, this is discrete. And that's because somehow in this pullback, I mean, I think it's kind of this, it's a much easier version of the cancellation thing that happens in the Hahn-Wilson regime that Piotr talked about this morning. So somehow everything cancels out in this limit and you end up getting something discrete. And somehow I feel like this is actually a fundamental result in mathematics, because somehow you can, I don't know, I mean, you can make some translations between this and the computation of the dual Steenrod algebra and the Siegel conjecture and so on. Somehow the fact that this actually happens lets you prove a lot of stuff. It can be translated into a lot of stuff. I mean, I guess both ways. You can prove it from these things, but you can also try to prove this directly. I mean, there are some sort of polynomial functor tricks to do that, and then you can deduce all these computations of the dual Steenrod algebra and so on from that. Okay, but then later, I guess, Bud Morrow-Scholzer sort of generalized this. We will not need this here, but let me just say this. I mean, for perfectoid rings, like something like OCP, you get, I guess, OCP adjoint X. Behaves similar to like what happens over FP for perfectoid rings. And then I guess you can also compute TR in that setting. And so let me say approximately, this is not quite true what I'm going to say now, but I'm happy to tell you why it's not true. But so what you get here is actually, this is going to be the Witt vectors of OCP, and then adjoint the Bott element, or V1 periodic element. So somehow here you see like redshift appearing. You see, you input this OCP, which is like a mixed characteristic version of FP in some sense, and then you end up having this spot element. And I mean, the reason this is not true is somehow because this is not spherically complete. You can either spherically complete that, or you get some lim1 terms in odd degrees that I'm ignoring at the moment here. Just, I mean, this would be true if you consider it appropriately as pro objects. Okay, so these are the classical computations. And what I want to be talking about now is not this base case. In some sense, I would consider these to be my K in my theorem. And then I want to talk about like smooth schemes or smooth algebras over the space thing K. So let's do that. And how do we compute like THH of things over base? And this is like the regime of Hochschild homology. This is a regime of the classical Hochschild constant Rosenberg theorem, HKR. So what does HKR say? So in the classical, I mean, this is like, in fact, the original paper is slightly more general than smooth, but I just, for simplicity, I want to stick to the smooth case. So R is again a smooth K algebra. Then what does this say? And let me say THH star R relative K. Again, this is the same as Hochschild homology. I just want to stick to THH notation here. This is isomorphic to the de Rham complex, R relative K. And what is R relative K? I mean, this is, I guess there are several ways of defining the de Rham complex. Basically, you first define omega-1 Kähler differentials, which has a universal property, and then you take the universal exterior powers on that. So as a result, this is going to be the initial strict CDGA with a map with a K-linear derivation. K-linear derivation. And what is, I mean, I think everyone knows what a CDGA is. It's a graded algebra with a differential. Strict means that the odd element is squared to 0. This is not forced if you're graded commutative, of course. And I guess it's clear what it means that the derivation, the derivative is K-linear. Okay, so that's a classical HKR theorem. And let me say a couple words of why it's true. And I want you to complement this statement here with this statement here. Right, this guy as an E-infinity ring is initial with a K-linear S1 action. And this thing here is initial with a K-linear derivation. And in fact, it's true that somehow the S1 action here, whenever you have a spectrum with an S1 action, you get some sort of a derivative d. In general, of course, d squared is not 0, but eta d, but okay, whatever. So in this case, because we are like living over ordinary rings, eta is 0. So this is going to be true. And so by this fact that this is true, somehow from this S1 action, you get a map from the right to the left by the initial universal property of this guy. And then, I mean, the theorem is about proving that this map is an isomorphism. And basically, you can actually even prove it using this universal property. You just, I mean, can by formal nonsense reduce, by étale descent, reduce it to the case of polynomial rings. And for polynomial rings, you literally use that somehow polynomial ring is free as an animated ring, and hence its S1 tensor will be free on the additive tensor of the generators with S1. And then if you know a little bit about how free animated rings on degree 0 and 1 generators look like, you get this result for free. That's basically a proof of this result, but I mean, I don't really want to get so much into details. I just want to say that somehow this being initial corresponds to this being initial on the homotopy groups. Okay, so that's a classical HKR theorem. And there is a version for THH. Not relative THH, but absolute THH, which I don't think is very useful to write down, but it would just describe THH star in terms of THHK. So roughly speaking, the version is if you know THH star K, you can compute THH star R in terms of that by just adjoining elements dr. And then it's not true that d of k is 0, but d of k is whatever it is in THHK. If someone wants, I'm happy to write down the result. So basically speaking, we somehow get these results, which are well known. Okay, what is the problem with this? I mean, this is nice, right? Like we just understand, I mean, we pretend we understand THHK and we want to understand something like THHR relative K. But now somehow I want to understand this with its cyclotomic structure in order to get my hands on TC, TR, and so on. And this is a problem because I guess it's basically two problems. The first problem is this relative THH is not a cyclotomic spectrum, so it doesn't really help me to understand like the cyclotomic structure having these homotopy groups. And the second problem, even if we ignore this problem, for example, by passing to the absolute case, the second problem is that this filtration by homotopy groups is also not very compatible with the cyclotomic structure. Well, let me say it like this. Tau less or equal n of THHR or tau less or equal n THHR relative K are not cyclotomic spectra. So as a result, if I just know these homotopy groups or these filtrations, I can't like really expect to learn something about the cyclotomic structure and be able to compute TC. That's a well-known problem, and I guess there are several ways of getting around this problem. First way of getting around this problem is considering the BMS filtration, which later has been generalized by Arpon, Jeremy, and Dylan to the even filtration. So the even filtration would be a filtration on THH while not being exactly through cyclotomic spectra. It's kind of compatible with the Frobenius in such a way that we can sort of leverage results from this. But there was another way, which is somehow the way that will lead me to TR today, that I suggested with Ben Antiu a couple years ago that I want to review now quickly. And that is somehow, I mean, you know, my favorite way of doing things. I mean, if something doesn't work, you just force it universally to work. That's what we're going to do here. And I mean, so how can you universally force some tau less or equal n to have some property? I mean, this is called a T structure. Just define it to be some adjoint. And then, okay, the adjoint will have to do what it has to do in order to make things correct. And that's what I want to talk about now. What did I want to leave on the board? Okay, and that's the following definition / theorem, just due to Ben Antiu and myself. Like 7-8 years ago. It says there is a T structure on cyclotomic spectra with the following properties. I guess with. First property is that the connective objects in this T structure, that's the only thing I can understand. So the connective objects are those cyclotomic spectra. Remember, cyclotomic spectrum is, among other things, a spectrum. And I'm just requiring that the underlying spectrum is connective. Underlying connective. Okay, so in other words, I'm declaring the functor from the forgetful functor from cyclotomic spectra to just the right T exact. I'm not getting right and left correct. Anyways, it preserves the connective objects. Okay, so that's okay. I mean, and it's very easy to prove that there is such a T structure. That's just the existence of some adjoint. This alone is not like saying a lot, but now somehow once you declare those connective objects, you have the co-connective ones, which are the right orthogonal of, I mean, cyclotomic spectra larger or equal 1, which has a suspension. And then, among other things, you have a reflection onto the co-connective ones. Just declaring that somehow immediately gives you a way of turning into any cyclotomic spectrum, somehow making some sort of truncation. It's just going to be the universal thing, which is somehow looks to be truncated in the cyclotomic world. That's what this T structure does for us. And the surprising thing is that now the things which are like connective and co-connective, so the things which are in the heart, these look very funky. These are not at all like discrete or something. For example, the object THHFP we've talked about, this is going to be in the heart. Right, so this is kind of, these are the, I just erased the homotopy group. This has like 1 FP in every even degree. So for ordinary like ice, it doesn't look very like co-connective, but for the cyclotomic ice, it is. That's what I'm saying here. And secondly, not only can we understand that, but we can understand like the whole heart actually. So how does the heart look like? So the heart is going to be the category of like derived V-complete Cartier modules. What is a derived V-complete Cartier module? A Cartier module is just an abelian group. I mean, the heart, by the way, I mean, most of you probably know this. The heart of every like stable infinity category with a T structure is going to be an abelian category. This is going to be an ordinary abelian category. And so it consists of abelian groups together with endomorphisms called V and F for Verschiebung and Frobenius, such that, so this is the whole structure, and what is satisfied, F after V is P. And secondly, I mean, this is what a Cartier module is, something that came up in like studying P-divisible groups in arithmetic. And then I guess V completeness is that the inverse limit over the V is 0. You can apply the V again and so on. And this is 0. And I guess I said derived V complete. Maybe I write R lim here, just to make clear that this is a priori not a limit in abelian groups, but like in chain complexes. And that has to be 0. Okay, so that's how the heart looks like. And that is, I mean, very surprising. And somehow, I mean, the way this equivalence is implemented, it sends like X, an object, a cyclotomic spectrum in the heart. This will be sent to TR, in fact. And I guess, I mean, I'm saying if X light in the heart, then the TR is discrete. So it's like TR0 of X. But really the whole spectrum TR, in the case X was in the heart, is discrete. And that's also how we can compute these mysterious truncations. What you do is you start with a cyclotomic spectrum, you can sort of form its TR, you truncate the TR, and then there's a way back. That's maybe the real content of that theorem. That there's a way back from like TR back to THH. That's kind of, in some sense, the real content of that result. Okay, cool. So that is somehow the cyclotomic T structure. And maybe the one example I will care about now is the one corresponding to taking pi naught. Unless there's questions. Other questions?
Is there a way to describe this just in terms of p-divisible groups?
No, I don't think so, because, I mean, not every Cartier module comes from a p-divisible group, right? So you can somehow put like finiteness conditions on the Cartier module and then it will, and somehow in the end, in examples there is a way of translating, but in general not. Good question. So, example, and the classical example, and this is the result of many people, I would say, like, is that somehow on the cyclotomic spectrum side, there's this P naught cyclotomic of THHK. Right, so I start with any, say, commutative ring K. I take its P naught cyclotomic, that's a cyclotomic spectrum. It will lie in the heart by definition because THHK is connective, and so I force it to lie in the heart. That's like the truncation. But then somehow under this equivalence, it will correspond to a Cartier module, and which one is it? I guess the most canonical one you can think of, namely the Witt vectors, the p-typical Witt vectors of that ring K, and that comes with operators called Verschiebung and Frobenius. And that's a Cartier module. And vice versa, from this Cartier module, you can cook up the cyclotomic spectrum. The homotopy groups look a bit funny, but somehow that's how the correspondence works. And that's somehow, in some sense, the base case of what I want to talk about. And, right, so what did Hasselholt-Madsen, and by the way, this is not only in some sense true for TR naught, but like all somehow homotopy groups in that T structure, you can just read off as the homotopy groups of TR. Right, so when you have an object in cyclotomic spectra, the cyclotomic homotopy groups are just the TR groups. I thought when we proved this was a really nice way of putting TR into perspective. What the role of TR in that whole story is. And the theorem that Hasselholt-Madsen proved, and really, I mean, Hasselholt does the math in his paper on p-typical curves, and then later it's stated in Hasselholt-Madsen that if R is a smooth FP algebra, then TR star of R, which by definition is TR of THHR. I'm just cancelling out one THH to not have to write too much, and which also would be like the cyclotomic homotopy groups now, in this sense, so of THHR. This is the Rham Witt complex. W omega star of R relative FP. And I think the Rham Witt complex is the last player in the theorem I had at the beginning on the board, about which I haven't talked. So let me talk a little bit about what the Rham Witt complex is, even though probably many of you know this already. What's the idea of the Rham Witt complex? You know, we have two constructs. I mean, in some sense, the Rham Witt complex, what you can do is you can assign to a ring, you can assign something like W star R relative K. The Rham complex, you can also assign the Witt vectors. And in some sense, the Rham Witt complex is a combination of the two. Like some sort of a weak push out here. Of course, it's not a push out in any reasonable sense, but somehow it combines the two things. Right, and so let me maybe say a couple words about the Rham Witt complex. The Rham Witt complex. And I think this was first introduced by Elucy over FP, or perfect rings of characteristic P. And I guess the same way that we define the Rham complex as some initial thing, you can also define the Rham Witt complex as an initial thing. So it's initial strict CDGA under, now not under R, but under Witt vectors of R with operations VF, which are operations from W omega star. So I want, I guess, yeah, let's say for FP, to W omega star R relative FP. V and F, and they have to satisfy a bunch of relations. What are the relations? Let me maybe, not so important, but let me say them. Again, we have F after V equals P, and we have, I guess, F is a ring homomorphism, so Fxy is Fx, Fy. V is a module map, so Vx, Fy equals Vx times y. And then you have relations of the sort Fd, P is equal to Df, and finally Vd equals Pvd, Pdv. Okay, these relations, I'm not going to explain why the hell one wants such relations. These are relations I just want. And then I can just make it happen. So, you know, like, say, I mean, this basically, you can write it down by a generators and relations description, right? You just throw in, like, everything you need to make it a CDGA over the Witt vectors of R. And then I'm just gonna quotient by those relations. That's gonna give me a huge presentation, but it will exist. And the reason this is like people cared about this, or Illusi came up with this back in the day, was that that this computes crystalline cohomology. Being cohomology in the smooth case. So crystalline cohomology is a cohomology theory that Grothendieck had introduced, and it was defined through a site. And back in the day, somehow people, I mean, notably Illusi, thought it would be nice if we could describe this like the Rham cohomology by a very concrete complex, and he achieved this by this exact complex. So I think it's very beautiful because, I mean, you know, you can write down stuff in differential forms as opposed to abstract side theoretic limits. Okay, so that's what the role of crystalline cohomology over FP is.
Sorry, maybe I'm a bit confused. So I think that in Illusi's setup, I mean, he come up with pro-FP complexes. So it's like it also has restrictions. But
yes, so you're right. So now Johan is like complaining that I'm being a bit cheaty here. So I guess, I mean, there's several ways of being a little bit more careful. So one way would be to say everyone here is V complete, and then it's a limit of the mod V to the n reductions. Or another way would be to say, well, this comes naturally not just as a complex, but it comes with truncations. There's truncated Witt vectors, and there's one complex for each truncated Witt vectors. And then the Verschiebung will go from the n truncated to the n plus 1 truncated, and the Frobenius will go from the n plus 1 to the n, and so on. So this is maybe the slightly more correct way of saying that. But it's equivalent to postulating a certain V completeness that I wanted to ignore here. Yes, thank you. Okay, so this is a Rham Witt complex, but this is in characteristic P, and then later it was observed that this in fact can be done in any over any base. And this is like a bunch of people who did that. Langer Zink first. Then there was input by Hasselholt-Madsen, who defined something called the absolute de Rham Witt complex. And then Mathieu, based on that, defines the relative one. So what's the outcome of these people's work? So this, the Rham Witt complex, makes sense over any base. Any base. Okay, I guess really Langer Zink said something P local, but this is also not necessary as we learned later. So it literally, and maybe unsurprisingly, if you just see my description, I mean, this just does make sense over every base, and you could just do it over every base. But the more important thing, and computes the appropriate version of crystalline cohomology. I'm not going to go into what that means in full generality, but so in the smooth case, it would compute that.
So are you saying that this is a definition? Or?
Yes, so I told you, I mean, the definition is just the initial thing with those relations.
Yeah.
Right, and I guess I should have said maybe dk is equal to 0. Dk is equal to 0, sorry. So it's for k in the Witt vectors of k.
Well, how does that make sense if we're not over a P local base, though? Are we still just requiring like P for Frobenius and for P very cheapo?
Yes, so one has to distinguish between two things. It's like P typical Witt vectors versus the ring being P local. These are the two things which are different. You can, of any ring, you can form the P typical Witt vectors, and of course you can always form the big Witt vectors. And I'm basically decoupling the two things. In the end, I can say little bit about the big Witt vectors, but somehow these are different P's. And I'm just always doing the P-typical constructions, but don't require anything about my rings. Yes?
And here you mentioned that K the base or I the ring?
K is the base, sorry.
Yeah.
So this is like, I guess, okay, so let's go back here. So they define something W omega star R relative K. And the point is the relative K forces the differential to be Witt vectors of K linear. So it's a complex over WR, and so it forces the differential to be Witt vectors of K linear. And so the Hesselholt-Madsen absolute thing wouldn't force that, but then you have to work a little bit around stuff with eta. But okay, that you can do. Okay, that is the format. I mean, the real theorem is by Langard thinks that it computes like crystalline cohomology whenever that makes sense. And okay, so that is, and so, but the problem is that TR star of THH R is generally not isomorphic to this de Rham Witt complex. And it's maybe not surprising because the left-hand side just somehow, I don't know, doesn't depend on K, whereas the right-hand side does depend on K. It's actually surprising that this is true if K is FP or K is a perfect FP algebra, but that is because somehow then secretly the right-hand side also doesn't depend on K, as one can prove by some sort of formally Étale deformation argument. So somehow this is just not true. On the other hand, we know that TR has somehow the necessary structure to produce a map from here to there, if you say it correctly. And so it has this V and F operators and stuff for which this is initial, except, I mean, not the K-linear one. So somehow what I'd like to put here is I would like to put the relative THH in order to make this theorem always true. But I can't, because again, relative THH is not a cyclotomic spectrum, so it doesn't make sense to form TR of that. And that's where this T structure comes into the game. And that's this kind of cyclotomic relative thing. Well, the definition is the following. So you form this THH R relative cyclotomic K. And the definition is just you take THH R. That's an algebra over THH K. The base, right? We're in the setting where R is a K algebra. I should have maybe written this again, but this is my standing assumption, R is a K algebra, and then I can form this is an algebra over that, and I can base change to this thing that I called pi naught cyclotomic, THHK. And that makes sense, right? So this thing here is somehow the best approximation we have seen exists to just forming pi naught of THH, which would be K. If I just put it K here, then I would literally, this tensor product would literally be isomorphic to THH R relative K. But here I put the closest thing that exists to THH to K, which is still like cyclotomic. And I put a little hat that will be central for a lot that I'm going to talk. So this is kind of a certain completion. This hat is a completion with respect to some filtration. Filtration on pi naught cyclotomic, THHK. So we'll in a second explain that there's a filtration here, and I can sort of, this induces a filtration on the whole thing, and then I'm going to complete with respect to that filtration. Okay, before doing that, I think I can write once on this board and then push it up. Let me make a bunch of remarks. So, I mean, first of all, of course, this is going to be the relative THH that features in the result up here. So I will state that a little bit more precisely in a second, but let's like just stare at it for a second. So the assertion is that this relative THH does the job and produces, like on homotopy groups, the Rham Witt complex. Let me just make a bunch of remarks before I state that again a little bit more carefully. So if K is FP, then it turns out that this relative THH, this relative cyclotomic THH, this is just the same as absolute THH. And that's somehow the reason why in the Hesselholt-Metzen result we didn't need this relative business. We just do absolute because it agrees with the relative one. And the reason eventually is, I mean, if you stare at this tensor product, I told you that THHFP lies already in the heart. So it will agree with this. And then, I mean, also the filtration is constant and you don't need to complete. It will just reduce to that. Secondly, the completion is almost always necessary. That held me back for quite a while. Initially, I hadn't seen this completion, and then I couldn't quite prove the result. And well, eventually, we realized there's this completion, and then you can prove, like, when is it necessary? So in other words, it could happen a priori that this thing is already complete before putting the head. But the assertion is this basically never happens. Like, for example, for an FP algebra, if K is an FP algebra, this will happen exactly if it's perfect. So exactly in the world where we know nothing happens anyways, something happens. For example, it's totally false for the integers or stuff like that. Okay, that's the second thing. And okay, so maybe now let me write a more precise version of the theorem I had on the board there. And that's, I guess, one version of that is due to Mao, and we have a slightly different version. And that, I mean, I guess the statement is in the smooth case, we have that the R of this thing is that. Right, so, I mean, this is correct. Let me not state it again. Let me just say what happens generally. Generally, for any K algebra R, I guess I could say animated K algebra R, but let's just say K algebra R. There's a filtration, is a complete filtration on THH R relative cyclotomic K with the graded pieces, graded N of this filtration, TR of that will actually be not quite the de Rham Witt complex, but the derived de Rham Witt complex. Omega star, omega, I guess, N R relative K. And then shifted in homological degree N. So what is the derived de Rham Witt complex? My plan was to not talk about this. You just define the de Rham Witt complex for polynomial rings, and then you take the left Kahn extension to all rings. Except you have to do that on finite level and do the limit at the end. There's some completion issues. But so this is kind of the standard thing we learned, like also if you want to state HKR or the even filtration or things like that in full generality, the standard trick we learned is first do it for polynomial rings and then left Kahn extend to all rings. That's what you can also do here. And then somehow in the case of smooth algebras or polynomial rings, it turns out that this derived de Rham Witt complex just reduces to the ordinary one. And this also, like, I mean, it's surprisingly subtle to get the completion right on the derived de Rham Witt complex. Okay, this is this theorem, and let me make a bunch of remarks about this result. I guess now I can erase this thing here.
In the smooth case area or polynomial case area, you're saying something about this recursive splitting.
Sorry again?
Erased.
Pardon me?
So in the smooth case, to get what you just erased, are you saying something about how this splitting, how this filtration splits?
No, I mean I'm saying then the derived de Rham Witt complex sits in a single degree. Right? I mean it's fixed n, right? I'm fixing the n. It's not. I shouldn't maybe say complex. It's the derived de Rham Witt sheaves, and then the n that's in a single degree. So the spectral sequence has to collapse. Yes. So that's what I'm saying. But somehow that, I guess, I feel like that's what we learned in the last years from a lot of people in the room, that somehow if you have something that works in the smooth case, most of the time there's just a filtration in general, which generally doesn't split. Even in HKR it doesn't split, despite statements in the literature. Okay, cool. Okay, let me make a bunch of remarks. So here's the reason I care about this, and I started thinking about this again. So what is the algebraic model for THH R relative cyclotomic K? By algebraic model, I mean the thing that should sort of filter this topological objects by means of a BMS-style even filtration. And the statement is that this algebraic model would be prismatic homology of R relative Witt vectors of K. If R is an algebra over K, then it's also an algebra over the Witt vectors of K. The Witt vectors of K are a delta ring. In joint work with Achim Krause and Ben Antio, we've defined prismatic homology relative to delta rings. So this left-hand term makes sense, and the assertion is that is somehow the algebraic version of that. And this is actually ends up being isomorphic to prism R mod P relative WK through a Frobenius twist. And this is actually, one can prove a crystalline comparison. This is R gamma crystal R relative Witt K. That's a generalization of Bud Scholz's crystalline comparison. I don't really want to talk about this because I initially wanted, but haven't found a way of saying these things in a way that are understandable within 5 minutes. Anyway, so somehow this is the algebraic model of what happens here. And I mean, in some sense, we were thinking about how to get a crystalline comparison of prismatic homology, or how to understand a crystalline locus in the Rham Witt stack, Cartier Witt stack, and that's in some sense the answer. And we came up with that from topology, from studying these TRs. That's why I sort of got back to the TRs. And let me also say that you can basically recover THH-R from can be filtered by pieces of the form THH-R relative cyclotomic K, and then with coefficients in the TR groups of K. So in some sense you can do this THH with coefficients, and then you can take coefficients not in K but in like the TR groups of K, and from this you get a spectral sequence converging to the actual TR groups or THH groups, and then upon applying Tatus 1 you also get similar filtrations for TP. So that gives you in general a filtration of absolute prismatic homology or the Cartier Witt stack by means of a crystalline locus. That would be the algebrogeometric picture I'm after here. And finally, I want to say we think that in some sense I want THH-R relative cyclotomic. Okay, I would like this to be an actual relative THH. And if you start thinking about the algebraic models, generally speaking, you can think about when something like a relative THH would make sense. And so morally, and this is just, I don't know, what's the moral color? Red? Maybe red's not good. Oh yeah, blue's good. Okay, so we want to think that this is something like THH-R relative some spherical Witt vectors of K. So if there exists a lift S WK of WK along S to Z. If there was a Moore spectrum, an E infinity ring over the sphere whose pi naught is the Witt vectors of K as a delta ring, then this would be true. And the question whether or not you can lift specific delta rings to the sphere, that's a question I think I've talked about here 2 years ago. I think still my knowledge about this is basically 0. I think I don't know a single delta ring which doesn't lift to the sphere. Almost certainly, I mean, for which I can prove it doesn't lift to the sphere. Almost certainly, this thing doesn't exist. So I again propose this as a sort of question. I think Robert Safarczyk, a student of mine, a master student of mine, had thought about this a lot. We could never ever like find an actual abstraction for doing that. If I give you any delta ring, say the Witt vectors of K, you ask whether it lifts to the sphere. And I would conjecture that this can only be done if K is a perfect FP algebra, in which case you can use the classical spherical Witt vectors. Anyway, so this is what I'm thinking. And somehow I would like to extend this whole picture to E infinity rings and the chromatic setting. But somehow, I don't know, I mean, it's not so clear how to define these relative versions, absolutely. And I think with the even filtration, Jeremy and collaborators have made such relative versions, or at least a decalage of these relative versions, very often possible, but somehow not in this generality to get a crystalline comparison, as far as I know. Okay, this is what I wanted to say about this. And so let me maybe end my talk by stating as a last thing a little bit about what this completion is. And since I'm basically out of time, I will give you a very sketchy version of that. So what happens, okay, let me say that in genuine equivariant world, because I think it might be actually that in this world, some people that have thought about this have already seen this and discovered that and just used different way of thinking about that. What you can do is somehow you can consider what some people call pre-cyclotomic spectra. That would just be and I say this in the genuine language, this would be a cyclotomic spectrum with a map from X phi Cp. Right, a cyclotomic spectrum would be one where this is an equivalence, but I'm just requiring a map. And somehow the non-genuine version of that would be what I call cyclotomic towers. The cyclotomic tower would just be a tower of spectra with S1 actions, like this, and now you have somehow cyclotomic Frobenius going from bullet plus 1 to X bullet plate Cp. So in other words, not every single term here would itself be a cyclotomic spectrum, but the Frobenius would shift. And that ends up being equivalent to this datum by just sort of remembering the geometric fixed points, because this map will give me a map like this. And what you can do actually is you can take the constant tower, and maybe the proposition is proposition on these categories. There's also a T structure, just characterized by saying all the underlying things will be connective. And in genuine land, I mean, we've seen this T structure, so it's just a thing which sort of just truncates all the fixed points. I mean, if you think of like genuine spectra as spectrum magnifunctors, there's an obvious T structure which just truncate all the fixed points. And that somehow would translate into something which looks a little bit more funky in this cyclotomic tower language, but again, understandable in terms of TR. And then somehow the result is that you can take this pi naught in this tower structure of THHK. And the statement is that this is a tower whose limit is actually pi naught cyclotomic THHK. And so doing everything in this tower language will automatically give me like that this pi naught cyclotomic is the limit of things. And then of course I can just define this relative thing here by just defining it to be the limit outside. Right, so it's like a completion. Question whether or not the completion is necessary is whether or not I can pull the limit out. Okay, Thanks very much.
Thanks a lot. Are there any questions? Go ahead.
Well, I had a question about what you wrote. Just it's a cyclotomic tower Python? Or?
This is like pi naught in cyclotomic towers.
Okay.
So, yes. So you just consider THH as a constant tower, and then you do pi naught, p naught in towers, that will result in a non-constant tower. It basically on TR is just a tower which exhibits its Witt vectors as the inverse limit of truncated Witt vectors. And then in fact you can prove I guess that's also what Mao does, you can prove a truncated version, how you get the truncated Rham Witt complexes from topology.
Is it clear from the tower perspective why the completion is unnecessary in the perfect case?
So, the completion is somehow, the question whether the completion is necessary is whether or not a certain limit commutes with this relative tensor product. Is that clear? So you define this relative TR, R relative cyclotomic K, to be really like the limit of somehow THHR tensor THHK with this pi naught cyclotomic tower THHK. And then the question is whether or not you can pull the limit inside, because then you would get pi naught. And so you can prove that you can do this for every THHR precisely if this tower is in every homotopy group Pro constant. Right, there's this kind of for every R, specifically for the polynomial ring over K, it's true that this can only be done if the tower is like homotopy group wise Pro constant. It's this kind of model structure, whatever, on Pro objects where you just declare the equivalences to be level wise or after truncations. And then you can analyze when this exactly happens. And if you look at, I guess, pi 2, you see that for perfect FP algebras, this exactly happens if the Witt vector Frobenius satisfies something, which I guess the Verschiebung is going to be injective, for example. Yeah, it's about Pro constancy of this tower. Yes, good question.
So maybe this morally part you mentioned, like goes this direction. So is there a universal property definition for THR, for this relative THH? Like there you took something over.
If you say something involving algebras, then yes. If you say something involving algebras over THHK, which you can say it as a functor, not for a single object, but as a functor. If you say for every K algebra R, there's an object which is an algebra over THHK, and which for K is cyclotomically discrete, and so on. I don't know a universal property description for a single object. And yeah, you can make such a lift, something which looks like such a lift, you can make it in a universal way. There's a universal E infinity ring with what I call a E infinity delta ring, with a map to that delta ring. It's just huge. Yeah, I don't know. I really would like to have someone come up with any obstruction to E infinity Moore spectra, which is not just pi naught is a delta ring. I literally claim all examples I know where you can obstruct the existence of an E infinity Moore structure, you can use the very simple obstruction that pi naught has to be a delta ring. And yeah, I don't know, for some reason, whenever I think about variants of the even filtration on cyclotomic spectra, I end up running into this problem that I can't lift certain things to the sphere. And of course, we've seen smarter ways around that, but I feel like the most direct way still hasn't been excluded in a lot of cases, even though it should be. Yeah.
Okay, I think we should stop here and thank Nikolaus again.